Family Math Tutor, Miss C here, and today we are evaluating and sketching the graphs of exponential functions. We're starting with the equation y equals 2 times 3 to the power of x. So before we can sketch the graph, we actually have to have some points to plot, and that is where evaluating comes into play. Sometimes teachers tell you exactly what points to evaluate or what x values they want you to find, the y values for. When you don't have that, you have to make the table yourself, and that's what we're going to do today. So I'm going to go ahead and create a t-table with x on one column and y on the other. And when I create t-tables, I just like to have about 5 values. You can always do more. The values should be positive and negative. So I'm just going to go from -2 to +2. And I'm going to start finding each value. So here's where we come in and evaluate. So evaluate is another way of saying substitute in your x value. So in this case, -2, everywhere you see x in the equation. So that's what I've done there. So you can see y equals 2 times 3 to the x, and I've substituted -2 for x, and then we're just going to simplify. So applying our exponent rules, we know that if we want 3 to the power of -2 to have a positive exponent, we drop it to the denominator, and we end up with 2 divided by 3 squared, which simplifies to 2/9. So when x is -2, y is 2/9. All right, let's do that again with -1. So everywhere we see x, we're plugging in -1. And when we do that, we're going to apply our exponent rule, and that 3 drops to the denominator. If you need a little help on negative exponents, I have an entire video on that. Go check that out. So when we plug -1 in for x, we got 2/3 out. Now, 0. So our parent function looks like this. Y equals a times b to the x, where a is our starting value or y-intercept and b is our base. So here's the deal. Since a is our starting value or our y-intercept, we know that when x is 0, y has to be 2. We could plug in 0 for x. Anything raised to the 0 power is 1. So 2 times 1 is 2. All right, let's do this one now. And we're just going to go ahead and plug this in. Everywhere I see x, I plug in y, 1. So 2 times 3 is 6, and we get 6 here. So you might be thinking, well, you know the base is 3, so why didn't you just multiply 2 times 3? So that's another way to do this. So instead of plugging in my next value, I could say, well, 6 has to be multiplied by 3 since this is exponential, and I get 18. So as a quick check, we know that 2/9 times 3 gives me 2/3. 2/3 times 3 gives me 2. 2 times 3 is 6, and 6 times 3 is 18. That's our growth by base 3. All right, let's graph this. So I've got my x-axis here and my y-axis here. Sometimes we're lucky and our values are labeled for us. Today they're not. So I'm actually going to go ahead and go by ones on both the x and the y-axis. And I am going to, on the y-axis, just label every 5. So here we go. Okay, you could also label every 2. It's up to you. I'm only going up past 18. And now I'm going to go ahead and start plotting my points. So at -2, we have y with a value of 2/9. It's a little bigger than 0. So here we go, right there. 2/3 at -1 is slightly bigger than half. So there we go. Our y-intercept is at positive, oops, not right there, +2. We have 1/6, which is right there. And we have 2/18 all the way up here. So I'm going to go ahead and connect these points into a curve. So exponential values form a curve. Looks like about there. And then this is going to go on forever. So we're going to put an arrow at that end. Now, exponential functions have something unique about them. And this is like this tail end right here. it's going to go on forever and it's going to keep getting smaller and smaller and smaller. So we went from 2/3 to 2/9, right? And then we're going to be at 2/27, and then it's going to get even smaller. It's going to get so small, but it is never ever going to equal exactly 0. And when our exponential curve approaches the x-axis but never touches it, there's a name in math, and that is called an asymptote. It's a weird spelling, hard to say. And what that means is my graph is going to come so close to our asymptote, which in this case is the x-axis, so y equals 0, but it's never actually going to touch it. It's going to look like it does, but it won't. So we want our graph to show that it's getting really close to the x-axis, but never touching. So there you go. This is your graph of y equals 2 times 3 to the x. Let's do another one together. This equation is y equals negative 2 to the power of x. So this is essentially a base 2 function. That means every value is going to double every single time. And then it's negated. Every value is multiplied by negative. So let's go ahead and set up our table, our t-table, and let's go ahead and find some values or evaluate for certain values and figure out what we get. So we really know that this negative, it's like saying there's a -1 right there. So let's go ahead and plot or jot down what our x-intercept is, and that is -1. All right, and then we know that we just double from there. So 2 to the power of 1. So the long way of doing this, like we did in the last one, is I'm raising 2 to the power of 1. It's 2, and then I'm multiplying it by a negative, so it's -2. So we're doubling here. We're growing by a factor of 2. And I know I can just double this value. Double -2, or -2 times 2 is -4. So this is growing by 2. If I go the other way, I could also think about -4 divided by 2 gives me -2. -2 divided by 2 gives me -1. -1 divided by 2 is -half. And -half divided by 2 is -1/4. So we can look, if we go down this way, we're multiplying by 2. If we go the other way, we're dividing by 2. Okay. Or you can just plug every value in. So let's go ahead and sketch this graph. So I'm noticing all of my y values are negative. So I'm going to go ahead and actually see if I can move my graph up a little bit. Since this is a negative, I need to go, there we go. So I'm going to go ahead and label, and I think I'm going to stretch this out a little bit, this graph, so it's a little bigger. So I'm going to label every other one 1. So I'm going up by 0.5s essentially. There. And I think I'm going to do the same thing on the y-axis. So I'm not even going to write the positive numbers. I'm just going to go down. And I'm going to do -1, -2, -3, -4. So the lines in between are 0.5. So let's go ahead and graph at -2. I have -1/4. So I would say that's about right here. At -1, I have about -half right here. At 0, I have -1. At 1, I have -2, which is right there. And at 2, I have -4, which is right there. So our asymptote for this graph is still y equals 0. So our graph is going to come like this. It's going to get closer to the x-axis. It's not a very good closeness. And then it's going to come down and curve through these points like so. All right, and it looks a little different than the graph that we did on the last one. It actually looks a little less steep, and that's because we stretched out our x and y values. It's actually very similar to the last one. It's just that we stretched things out when we did our scale on our axes. All right, which I should have labeled as x and y. So sorry about that. All right, let's do one more. Our final problem in this set is y equals 10 times half to the power of x. So we notice that our base is half. That means all of our values get cut in half. And let's try to do this without doing substitution. So we can just do this using our knowledge of exponents. But as a reminder, you can always substitute any of these x values in, and you will get the correct answer out. So here's the deal on this one. Let's start by putting in our x-intercept. We know that's this number right here. So it's 0, 10. So when x is 0, I have 10 left. This is cutting in half. So my next value is going to be half of this. So I'm going to get 5. So if I were to write this out, I would have 10 times half, which is 5. So that's how I'm getting that. And then the next value cuts in half again, and half of 5 is 2.5. Okay. Now, 10 had to be half of a value, and it was half of 20. And then 20 was half of a value, which is 40. So if I were to look at this, 40 times half is 20. 20 times half is 10. 10 times half is 5, and so on. Okay, so our range is going all the way from 2.5 to 40, but actually we know this graph is more infinite than that. So let's go ahead and get labeling here. I think that we will go by, I'm going to go every 2 here. So I'm going by 0.5s here. Sorry about that. I'm labeling every other one. So I'm going by 0.5s, and I'm labeling from -2 to +2. On the y-axis, I think I'm going to make, got to go up a lot. I'm going to make every 3 lines equal to 5. So that's 5, 10, 15, 20. Hope I have enough room. 25. Oh no. 35. Guess I should have planned this out better. 40. It always happens to me when I graph. I never quite go far enough. You can make your scale whatever you want. You can list as many as you want. You just have to have the same scale on the y-axis. So every number of units you go up on the y-axis has to be consistent, and then the x-axis has to be consistent across. The x and the y-axis do not have to have the same scale. Okay, so let's go ahead at -2. I'm clear up at +40. There we go. At -1, I'm at 20. At 0, I'm at 10. At 1, I'm at 5. And at 2, I'm at, well, this is going to be interesting, 2.5 right there. Okay, we know our asymptote is still y equals 0. So we're going to have our graph, and it is going to basically do this. It's going to get really close to the x-axis, and our curve passes through all those points. Okay, and that is our curve. This is a decay curve because our base is between 0 and 1, non-inclusive. So our exponential function is decreasing or decaying. Thank you for joining me as we evaluated and sketched our exponential functions. Till next time, remember, you've got this, and don't forget to subscribe.